Picking up with part two, physics, week four, going over circular motion, we were talking about centripetal acceleration being an acceleration because it's changing a direction as it moves in a circle. But any acceleration has to have a force acting on it. So, what is the force that causes it to move in a circle? It's a centripetal force. But the force is always acted towards the center. So, any question they're going to ask you and say, what direction is the force? It's always inward, it's never outward. So anything moving in a circle, the inward force is what you want. Now, as I said in the last segment, there is this centrifugal force that is a perceived force. It's not a real force. It's due to inertia, the tendency of a body to move in a straight line path. The problem is you're not moving in a straight line path, so there's something that makes it feel like you're being pushed outwards. It's not a real force, though. It's just inertia. Think of if you're in a car moving, going real fast around a corner. I remember sitting in the back seat and, sliding all the way across to the outside. Technically, that's not a force pushing me that way. It's inertia wanting me to go in that tangent, in that straight line going away. It doesn't want to turn direction. So you need a force that makes you turn that direction. That is the difference between centripetal and centrifugal. It is the effect of the rotation. It's not a real force. And that's why I said it's a perceived force. You put it in quotes if you want, because there is technically no action reaction in order for it to be a force. If you remember from chapter 6, when we were talking about forces, force has to have an equal and opposite force. And action has to have a reaction. In this case, the fact that you're wanting to be pushed outside of the car as it rounds a corner, it is inertia that's doing it. It's not an actual force pushing you. So then if you don't have a force, you can have an equal and opposite force acting on it. All forces must occur in pairs. In the example, as you were going around that corner, what's causing the car to move around the corner is the friction in the tires. Think about if there's ice, you keep going straight because there's no friction to create that centripetal force that's going to cause you to turn and change your direction. Now, if we get into chapter 11, which is rotational motion, we just kind of include some of the things from those chapters into circular motion again. But inertia was one of the things we talked about, and anything moving that has mass is going to have inertia, whether it's going to want to start moving if it's at rest or if it wants to stop if it's already moving. Anything moving in a circle has the same thing. So we just call it rotational inertia. And it's the idea that a body that's not rolling doesn't want to, or a body that is rolling already is going to want to continue rolling. And that's basically just adding the idea of inertia into the fact of something that's moving in a circle or rolling in this case. Now, rotational inertia is depending on how far the mass is away from the axis. I'd take you down to the gym and we could do this if we were in school. But if you take a dumbbell that has the weights very close together, same amount of mass between these two weights, but if they're close together and you just try to rotate it or spin it, very easy to rotate, which means it doesn't have a lot of rotational inertia. The farther you take that weight and spread it out away from the axis, the harder it is to rotate, which means it has more rotational inertia. So a couple of questions that they will ask you that I'll ask you in your questions that you have on here, it has to deal with rolling. Well, the more rotational inertia means it's not going to want to start going. And if it doesn't want to start going, it's going to accelerate down a hill slower. So we look at a couple of different things. It's the laziness, as we said, it's not wanting to start going. And as it starts going, it means the one that has lower rotational inertia will actually roll down a hill faster and have greater acceleration. Solid, why? Because look at where the mass, these two things weigh the same mass, but this is farther away from the axis, which would be right in the center. So it has more rotational inertia, which was going to cause it to roll down the hill or the incline slower than a solid disc. Even though it has the same mass, it's more closer to the center of gravity. And we would talk about the same thing on a bike tire and moving, or a cylinder versus a hollowed out, a pipe. They would end up doing the same thing. Though the farther, more rotational inertia you have, the slower it's going to roll